Well, thank you very much. It's great to be here. I don't know if all of you know, but I don't actually work up here in London. My department is out near Guildford, so it's a bit of a trek from the countryside to come in here today. But I work in UCL's Department for Space and Climate Physics, and we are a department of 150 space scientists and engineers who build space instrumentation, launch it with the major space agencies all around the world, and then do research with those instruments. So I'm lucky enough to work with lots of exciting people in NASA, the European Space Agency, and also the Japanese Space Agency as well. But what I want to do today is give you a bit of an overview about what the sun has been up to recently. So I'm not sure, hands up if you've heard anything in the news about the sun over the last year or so. Any news stories? Most people have, right? Which is great. I'm very happy to hear my research area being talked about in the public news. And to me, the news stories kind of fall into two camps. So on the one hand, there's been lots of stories saying that the sun is going to produce a huge burst of activity that is going to destroy electricity networks all around the world, which would not be good for us. On the other hand, people have been saying that the sun's activity is going to completely switch off, and that's not so good either. So what I want to do today is talk a bit about the sun's activity, what is happening, what isn't happening, and then also talk about my research area, which looks at one particular area of activity. I think I'm lucky enough to study some of the most beautiful events in the sun's atmosphere, so I thought I'd show you, as first off, a nice movie. So these are the kind of events that I study taking place in the sun's atmosphere. So this is a huge eruption of material coming up from the sun's surface. In fact, this is my favorite eruption so far that the sun has produced. I've been studying the sun for about 14 years now. And this one happened in June this year, and it was absolutely spectacular. So this is a movie that I made using data from the NASA spacecraft called Solar Dynamics Observatory, and anyone can go online and have a look at the data coming back from this satellite. Absolutely spectacular. So what we're looking at here is a huge eruption of hot gas, plasma, ionized gas, and also magnetic field from the sun's atmosphere. And I'm going to come back to this again later on. The technical term for these eruptions is a coronal mass ejection. I always have to be careful when I say that word because people tend to snigger in the audience. You're a very polite audience. I was talking to, or I was being interviewed on the 10 o'clock show earlier this year by Jimmy Carr, and we were talking about coronal mass ejections, and he found it utterly hilarious that this was the name of these eruptions. But actually, it was quite exciting during January this year when the BBC Stargazing Live programme was on, because the term coronal mass ejection trended on Twitter. I don't know how many Twitter users we have in the audience here, but I was very, very excited about that. And that happened because Jonathan Ross mentioned on Twitter that he was afraid of coronal mass ejections. I don't think that's ever going to happen again. But actually, we should be worried about these eruptions, because when they move away from the sun, they carry charged particles, plasma, and the magnetic field of the sun with it. And if they come towards the Earth, they can interact with the Earth's magnetic field and set up a complex series of currents in the Earth's magnetic field and also through the Earth's rocks. And that's where the effects to our electricity networks come in, our navigation systems, communications, aircraft, things like that. So actually, these eruptions of what you can see happening behind me do have a direct relevance on our lives. And people like myself and colleagues all around the world are watching these eruptions to see what they're doing and to see if we can forecast what the effects will be on the Earth. So this is the kind of way that I look at the sun, using these kind of images. This is actually an ultraviolet image of the sun taken from a satellite which is far above the Earth's atmosphere and allowing us to pick up the ultraviolet light being emitted by very, very hot gases in the sun's atmosphere. But from the ground, as you people do, we see the sun in a very different way. And we see the sun in visible light that our eyes can detect. And in that case, the sun looks like this. Totally different. These two images are taken at exactly the same time. So here, where we have bright regions, if I go forward again to the visible light, not quite sure why the sun's oscillating there, but you can see where the bright regions where we have sunspots in our visible light image. And most of what I want to talk about today really is to do with these sunspots, because the sunspots are the main driver of solar activity. So I want to talk about what they are, how they've been changing with time, and why they're so important. So these dark features on the surface of the sun are sunspots. And actually, the first records of sunspots go back well over 1,000 years. But to get really good observations of them, we needed the invention of the telescope. So the best records of sunspots date back over the last 400 years. And I thought I'd show you these sunspot numbers. So like any good scientist, I'm going to show you a graph. So here we have our graph. We've got sunspot number up the y-axis, and then the year along the bottom axis, the x-axis. So going from the early 1600s when the telescope was first produced, and then coming up today. And we can plot our sunspot number on here. And you'll see that the sunspot number rises and falls over a fairly regular period. In fact, each one of these cycles lasts, on average, 11 years. So this gives us the sunspot cycle. And you can see the number, well, in fact, here, rises and falls, and then switches off. So we had the invention of the telescope, good observations of sunspots, and no sooner had we done that, the sun decided to stop producing sunspots. So in about 1645, we had several decades where the sunspots disappeared. And we call that time the Maunder minimum. And that's after Walter Maunder, who was an astronomer at the Greenwich Observatory in London, who was one of the people to point out that maybe this is a significant feature on the sun, and we should be trying to understand why the sunspots switch off. So that's the Maunder minimum. Huge amount of interest in the Maunder minimum. Lots of people like to link it to climate change on the Earth. I don't agree with that, but we could talk about that at the end. So there we have the sunspot cycle. And let's have a look at some sunspots. So these are sunspots as drawn by probably the most famous observer of sunspots, Galileo. So in the early 1600s, actually these drawings are from 1612, he had his telescope, he projected an image of the sun, and every day he went out and drew the sunspots that he could see through his telescope. So what you'll see is that day by day, these sunspots are moving. And actually, you can get a sense of the rotation of the sun from them. So the rotation axis is coming down here. But it's very easy for me to talk about sunspots as being on the surface of the sun. Back at the start of the 1600s, with these early drawings, it was contested. How do you prove that these are features on the surface of the sun and not maybe planets in a close orbit around the sun, or maybe even clouds in the sun's atmosphere? So a lot of work was done to prove that these are actually features on the sun's surface. And then I can bring us up to the modern day, and we can have a look at some of the best sunspot observations. So here we have an image of a sunspot group taken actually from the Earth's surface using one of the best telescopes that we have, the Swedish Solar Telescope. Absolutely amazing pictures. So now, rather than just being black blobs, they've got a huge amount of structure in them. So in the center, you have a dark feature. It's called the umbra. And then outside, you have this sort of like flower petals coming out, and that's what we call the penumbra. And then even you can see in the surface of the sun itself a lot of structure. It's very, very mottled. So this is the classic view that we have of sunspots now. And in fact, they appear dark because the gases in these sunspots are relatively cool compared to the surface material around them. So we've been looking at sunspots for, well, in detail, for 400 years. But the big discovery about sunspots came in 1908 by an American astronomer called Hale. And he made a huge step in our understanding of the sun. And I can't stress how important this discovery was. He was able to build a telescope to study the sun that could pick up the fingerprint of magnetic fields elsewhere in the universe. The sun was the obvious object to look at. So at this point in time, we only knew that the Earth had a magnetic field. We didn't know about any other magnetic fields in the universe. And he made a telescope that could pick up magnetic fields, pick up the signature of them, and he pointed it at these sunspot regions. And what he found was that sunspots are sources of very strong magnetic field. And in fact, when you look at sunspots, you'll see that they occur in pairs or groups of pairs, and one will have a north pole and one will have a south pole. And on the right-hand side here, I've got my classic bar magnet. I'm sure everybody has played with the bar magnet, so I hope so, and sprinkled your iron filings over it. And the iron filings take on the shape of the otherwise invisible magnetic field lines. So what we will have emanating from our sunspots at the surface of the sun are invisible magnetic field lines connecting one sunspot to the other sunspot. So Hale enabled us to realize that the sun is a magnetic object and that these sunspots are sources of magnetic field. So I want to show you the kind of data that I work with. On the left-hand side, I've got your typical picture of the sun as seen in visible light. But what we want to do is to be able to measure the magnetic fields in the sunspots. So we can make a telescope that is able to do this. These images are taken from, again, the Solar Dynamics Observatory, this NASA spacecraft. So what I want you to notice is that on the right-hand side, the picture is basically black and white. The white regions represent places where the magnetic field has a north pole and is coming out of the sun. So it's a source of magnetic field. The black regions are places where the magnetic field is going into the sun, so it's a sink of magnetic field. And if you look, you'll be able to see that where that sunspot, these sunspots here, correspond to these very strong sources of magnetic field. But what I'd also like you to notice is that actually the whole of the sun is covered in black and white spots. So even outside of these sunspot regions, you have a lot of magnetic field, even though it's more dispersed and it's weaker and it's in smaller size scales. But you can see here, huge patches still with these black and white spots in them. So I started off talking about this eruption and then went on to talking about sunspots. And what I want to show you now is that these two things are heavily related. If I show you this is my eruption happening seen in ultraviolet light. If I show you the white light image, we can see where the sunspots are. So you can see this is the region where the eruption is taking place. It's coming from a sunspot region. I can show you my magnetic data. Here's the magnetic field. So the point I want to stress is that these sunspot regions are sources of very strong magnetic field. That magnetic field actually carries energy with it, and that energy leads to activity like these coronal mass ejections. So when we see sunspots on the sun, we get very excited because we know that the sun is about to start doing something very interesting. It's also good for my research because these are what I study. So we have sunspots on the sun, they produce activity, and the number of sunspots varies over time. The question then is, well, what's going on? Where do these sunspots come from? Why do their numbers vary? Why do they sometimes switch off? To start to answer these kind of questions, we need to look inside the sun, which is a very difficult job to do. We can't see directly inside the sun, but we have a really incredibly useful technique that's called helioseismology, which uses the fact that the sun actually rings like a bell. And we can measure these sound waves at the surface and use that to extrapolate and get information about what's happening inside the sun, which is absolutely fantastic technique and has been so important in understanding the sunspot cycle. So to show you what I mean, I've got a picture of the sun here with a cutaway. So we've got, this is all real data, I should say. So the picture that you can see of the sun here, you've seen that all before. This information in here has all been gathered by helioseismology. So picking up the sound waves at the surface and probing what's happening inside the sun, in particular, what the flows of plasma are like inside the sun. And the bands represent different flows. And what's nice is that you can very easily see there's an obvious zone here. Oh, it's disappeared. Hopefully that will come back. Anyway, I'll carry on. So what you could see, hopefully will in a second, yes, is that there's one obvious zone here. We call that the convective zone because of the way energy is transported in that region. And then you have a strong line signaling a transition in flow speed going into the sun. And this region in here is called the radiative zone, again, because of how the energy is transferred. So this makes a very nice schools talk, actually, talk about the different mechanisms of energy transfer inside the sun. And actually, what we've realized is that this zone is incredibly important for understanding why sunspots are formed. And what I want to do now is show you a couple of animations to try and illustrate that process. So, we know that the sun is a magnetic object. We can measure that. And we know that, similar to the Earth, the sun has an overall dipolar field. So you'd be familiar with the fact that the Earth has a north magnetic pole and a south magnetic pole. The sun has exactly the same, which means that our magnetic field lines are aligned north-south. So what this movie has done is it's gone inside the sun. So we've gone in to, I go back, we've gone into this shell inside the sun. And we've represented the magnetic field lines as being aligned north-south. Now, from helioseismology, we can get the flow speeds of the material inside the sun. And we also know that because the sun is made of a plasma, if the plasma flows, it takes the magnetic field with it. So it's like having an elastic band and stretching it and twisting it. So what happens to the magnetic field? Well, we know that the sun rotates faster at the equator than it does at the poles. So if we let our movie run, those magnetic field lines get stretched out and wound up around the sun. And this is a very, very successful model. And you can see that you have two bands where the magnetic field has been amplified. If we let that process run on even more, it gets more and more amplified, and the magnetic fields become so strong they can't stay inside the sun, and they become buoyant, and they rise up, and they come through the surface and into the sun's atmosphere. And where they intersect the surface is where you have your sunspots. So the sunspots are the intersection of very, very large magnetic structures that ultimately were formed inside the sun and became buoyant and rose up. So you can kind of visualize that here. So if we take this loop, the sunspots would be at the feet of this loop in the surface of the sun. So let's have a look at some observations of this magnetic field coming up and forming our sunspots. This is a movie showing sunspot formation. This one is a pre-existing, and then new sunspots form here. So I've zoomed in to the surface of the sun. I'm just looking at a small sunspot region. So there we have the sunspots forming. They appear, they grow in size, and they separate as this arch of magnetic field comes up from the solar interior. Let's have a look at what happens in the atmosphere. Because before I mentioned if you have your sunspots, you should have arched field lines connecting one sunspot to the other. But how do we see that in the absence of being able to go to the sun and sprinkle our iron filings over it? Well, luckily for us, the sun has iron gas and other gases in the atmosphere which trace out the magnetic field lines for us. And we can see them like this. So this is the emergence region here, the sunspot region, and you see those arches connecting one sunspot to the other. And suddenly the sun looks much more three-dimensional. So very, very clear indication the sunspots are the feet of those magnetic arches. Right. But I don't want to look at the sun just on the timescale of a few days, which is what I showed you there. To understand this sunspot cycle that's been going on for millions of years, I want to look at the sun for as long as I can. And we're just coming to the point where we're getting several decades of observations now that we can put together. So the movie I want to show you now is a full sun movie, looking at the magnetic fields in these sunspot regions. So before I had black and white, now I've got yellow and blue. Interesting to note that the sunspots form two bands above and below the equator, as predicted by that wrapping of the magnetic field. Perfect. And what I'm going to do is run this over time, so you'll see the sun rotating. But what I'm going to do is stretch out the sun, so unwrap it, so that it becomes a flat surface. So here, enabling us to see the whole surface of the sun at one time. And then I'm going to show you how the surface of the sun changes with time. So going from 1980 up until today. So the magnetic fields disappear at sunspot minimum, and then they come back again. And they'll disappear, and they'll come back again. So this is showing us that the sun goes through this cycle where magnetic fields amplified inside the sun rise up into the sun's atmosphere. And it goes on again and again and again. Magnetic fields come up, they die away, things go quiet. A new bunch of magnetic fields comes up, they die away, and so on. So every 11 years, this cycle is happening. And of course, with this solar cycle, with this sunspot cycle, each sunspot emergence brings with it magnetic field, which actually has energy in it. And that energy is released through solar activity, like coronal mass ejections. So the coronal mass ejection frequency follows the sunspot cycle. And what I find particularly interesting about these eruptions is that, okay, they're interesting in their own right, but they're crucial for the evolution of the sun. Because if you had a continual, well, we do have, an emergence of magnetic fields into the sun's atmosphere, going on and on and on, what happens to that magnetic field? It would endlessly accumulate, and in particular, the energy contained in that magnetic field would endlessly accumulate. So if you didn't have coronal mass ejections erupting material into the solar system, the sun's energy would just keep increasing and keep increasing. So CMEs are absolutely crucial to provide a valve for this energy in the sun's atmosphere. And I think they're a natural product of this process happening deep inside the sun that creates these magnetic fields or amplifies magnetic fields. And we call this amplification of the magnetic field the solar dynamo. So, what do I do? My job is to understand why and how coronal mass ejections happen. When I first started, or when I first realized that these eruptions take place, I was completely fascinated by them. They erupt the mass of Mount Everest into the solar system at velocities of up to, well, the fastest one I've seen was traveling at 2,000 kilometers a second. How does that happen? I just thought that was fascinating. These structures are huge, many, many times the size of the Earth. Where does that energy come from? Why does the sun's gravitational pull not keep these structures on the surface of the sun? So my job is about understanding why and how they take place. So what we know is that as the sunspots are formed due to magnetic flux coming up from the interior into the atmosphere, we see arches. So the sunspots would be at the feet. Now, these are the fundamental building block of the sun's atmosphere in which coronal mass ejections occur. But coronal mass ejections come towards the Earth, they pass over our spacecraft, and we can measure the structure in the magnetic field. So we can see, does it have a loop-like shape or does it have another shape? And actually, it has another shape. So this is where I'm going to start gesturing, because what we measure in space is that the magnetic field carried away from the sun doesn't have a nice, simple arch shape. It has a rope shape. So you've all seen a bit of rope which is twisted. And that's what the magnetic field lines are like in coronal mass ejections. So they are like huge ropes that are tied at two ends to the sun and extend vast distances all the way to the edge of the solar system. But the magnetic field lines are twisted, forming a rope. So I've got a computer model of what such a rope would look like in the sun's atmosphere. So hopefully you can see that these field lines, these are just computer-generated field lines. This is real data here, the surface magnetic field, but these coloured field lines are more twisted, and they produce a rope. So what I'm interested in is finding these ropes of magnetic field in the sun's atmosphere. So how do we look for them? And in fact, if you have a rope of magnetic field, we understand how it can erupt quite easily, actually. We can do it in a laboratory simulation, and we can also do the physics in the sun's atmosphere. So the observational support of a flux rope, magnetic flux rope at the Earth, plus the physics of knowing that these structures can erupt if they are in the sun's atmosphere is quite compelling. So what I do is I look for S-shaped structures in the sun's atmosphere. And here are a couple of computer models. So what they show is a magnetic flux rope that's vertically aligned here. And you can see some twisted field lines in the middle. But the important thing is that at the edge of this flux rope, if you imagine there's magnetic field lines that make one complete turn around the flux rope, so here, it goes over the top, under the bottom, over the top, those field lines have an S shape. And we know from theory that plasma or gases trapped on these field lines should be heated to very high temperatures, and they should emit in X-ray radiation. So one of the things I do is I go to the sun, I look at the images, and I see, can I see any S-shaped structures? And of course, yes, I can, otherwise I won't be talking about them. So here is one of those S-shaped structures. So this is now looking at loops in the sun's atmosphere using an X-ray telescope. So the gases trapped along this S-shaped structure have a temperature of about 2 to 4 million Kelvin. So very, very hot. This is an outline of the S-shaped structure overlaid on my sunspot region, where I've got the positive or north pole and negative south pole. So my job is to look for these structures, identify magnetic flux ropes in the sun's atmosphere. Just to quickly show you another data set. So this is one of my favorite ones. And this is, again, the loops in the atmosphere, hot gases trapped along magnetic field lines above sunspot regions. And it shows one particular region evolving over about a day and a half. This is where the sunspots form, and these are those arch-like field lines that we saw in the earlier on image. Nice loops. But as we watch this over a few days, or a day and a half, you can see that the magnetic loops, which is really what we're seeing here, change their shape until they end up with an S-shaped structure. So what we're seeing here, what we're able to infer, is that the magnetic field comes up, it produces an arch-like structure, and then it evolves and changes with time, and it stops being an arch and ends up being a twisted flux rope. So these are the kind of observations I use to A, find the flux rope, but B, work out how it formed. So how much magnetic flux goes into it? What is the configuration of the magnetic structure itself? And all these things are important because this erupted a day later. Had it come towards the Earth and hit the Earth's magnetic field, its exact magnetic configuration will determine how much the Earth is affected by it. So it has to have the right kind of magnetic configuration to strongly affect the Earth. And by doing this kind of research, I can be able to say, well, okay, this structure, when it erupts, it won't make any effect on us, or it will, and the electricity networks and airline industries and so on need to pay attention. So my research is all about understanding the magnetic structures in these coronal mass ejections. Right, okay. So I think I've got a couple more slides now, so I'll wrap up quickly. Just let's have a finish on what the sun is due to do in the future. So is the sun going to produce a huge amount of activity and destroy life around the Earth? Or is the sun going to switch off and destroy life around the Earth? Or is it just going to carry on as it has been doing for 4,500 million years? So this is the sunspot number that we've looked at. Here is where we are today. Let's do a zoom in. So this is the latest data coming from the sunspot number count. And anyone can go online and have a look at this data. So this is the solar cycle that we've just come out of. This is cycle number 23, so that's this one here. And actually, it was a really interesting cycle. As it progressed, it seemed like it was nothing particularly different. But as it ended, as the sunspot number faded away in sort of 2007, 8, and 9, we came to solar minimum, and the sunspots just seemed to disappear for much longer than we were expecting. So we had what we call a very deep solar minimum. And actually, the sun hasn't been this quiet for about 100 years. So the sun really seems to be getting quieter. But the sunspot number did pick up again, and here we go up, and this is the prediction for the next sunspot cycle. So we are having a sunspot cycle. There are coronal mass ejections and other activity coming from these sunspot regions. So the sun, the sun isn't switching off. These sunspots are still here. But because the sunspot number is on the increase, we are having more coronal mass ejections. And more coronal mass ejections means we're more likely to have effects on the Earth, to our electricity networks and so on. So it's kind of, the stories that you've heard in the media are kind of a little bit correct. Yes, the sun has been quite quiet, but the activity is picking up, if that makes sense. And we're predicted to have solar maximum in 2013. So I think I'm coming close to the end of my time. But what I wanted to show you is that to understand what the sun's doing, what modulates this sunspot cycle, we need to see what's happening inside the sun. And I love this movie. I'm going to show you some real data from helioseismology. This is the surface of the sun with the sunspots. And as the movie runs on, the sun will be opened up, and you'll be able to see the flows inside the sun as computed from this data. So here we go. So the sun is rotating. It opens up. There's a huge amount of complexity in there. So here we have fast flows going around the sun that wrap up that magnetic field, produce strong field that creates the sunspots. But what I really love is this. These flows here, like a conveyor belt, coming from the pole down towards the equator, coming to the surface, and going to the pole again. And we can measure these. And we can measure how they change with time. And actually, that's what's been happening in the last few years, is that scientists working for NASA have detected changes in these flows. And it is these flows that modulate the sunspot cycle. So that's what's happening inside the sun. Changes in flows which affect the drawing out of this magnetic field, and it's reprocessing through the sun. Oh, it's running again. So these flows here take sunspot magnetic field and take it up to the north and south pole of the sun and reprocess it into the next solar cycle. So these flows are behind the sunspot cycle, and understanding these flows will enable us to be able to understand exactly why the sun produces cycles of different size scales and so on. So my last slide is to say that it is these flows that control the solar dynamo and produce this sunspot cycle. So the flows will be responsible for the sunspots switching off here. The flows will be responsible for creating particularly big cycles here, here, and here. And just notice, actually, now, these sunspot cycles seem to be diminishing in size. So in the coming decades, I would think we will have smaller sunspot cycles. We call this coming out of a grand solar maximum. So there's all kinds of frequencies of periods in this sunspot cycle. So something that's seemingly so simple, just counting the number of sunspots on the sun, actually tells us something very, very fundamental about how the sun operates. So I think I will finish there, and I think we will have time for a few minutes of questions. So thank you for listening.